All right, okay. So I'm going to talk about everything now, every physics now, the gravity. This is the apple.
Engang.
Yes.
On the
Oh,
chin.
sorry. Okay, yes.
Right on. Touch it. Touch it on the chin.
Okay.
No, closer, closer.
Closer.
That's it. Yes.
Thank you. Right. So we all heard this story about Newton's story. So he formulated the the formula. So that's Newton's gravitational law. So everyone knows. So we start this one from high school. All right. So also the great scientist Albert Einstein also formulating this kind of gravity as the curvature of space-time. He put that very complicated equation there. And also currently we have a lot of great scientists, physicists working on this problem. You've probably heard of quantum gravity, or string theories. All right. Because now we are in the past, we're not going to talk about this complicated thing. We're going to focus on that simple formula to say, so if we really understand gravity, right? That's my task, right? All right, so let's look at the formula. So basically that formula tells us, so the force, gravitational force between two objects, m, small m, and the big M. So you can calculate that. So now up here, so I have three sort of setups. So we have 3M, so over there, and the big M's. So they always with different shape, but they're always the same total mass. Right. By looking at the formula, so let's now ask you the algebraic question in the audience. Are the gravitational force in the three cases going to be the same by applying that formula? So if you say yes, put your hand up.
All my questions.
All right, okay, the condition is we have the same small m, same big M, same R, so the answer is going to be the same. But what we're going to show you, you're all wrong. All right. That's basically, hopefully with this kind of presentation, we can have a little bit understanding of the gravitation. Right, that's what we're going to demonstrate. Now, so if you look at, after Newton put the gravitational law, he spent probably another 10 years to work on another thing which we call the Newton theorem. So for Newton theorem, so you can have this only when you have the spherical mass. So you can utilize that formula. Otherwise, so you have to calculate that.
Wow.
Right? So that's why, okay. So now, the following question is going to be, can I ask you, for those who think, so they are different with these three different situations, so which one, the gravitational force, is the largest? So let me say, okay, put your hand up if you think this one is the biggest. If you think this one is the biggest, this one here. Right, let's find the answer. Right, so the answer is going to be, we have to, with this formula, if it's not spherical, you cannot use that simple formula, you have to use this one here. What you can do, you have to use the computer to calculate. So you have to find that mass distribution, you have to know the shape, right? So for this one here, I have a spherical, I have a disk, and I have a bar. So basically, with this one here, so you can utilize that formula, that simple formula. But for that too, you can't. So you have to calculate by using the fun numerical. Here's some result. The answer is going to be, so this case is stronger. So that means with the same mass, so same total mass, so when you have different mass distribution, you're going to have a completely different gravitational force. So how much? For example, if we compress this spherical to a disk, you have a few times larger gravitational force. So that's basically, so what's the impact of this? So if you look at this solar system, so we know for the solar system, so the sun is spherical, all the planets are spherical. So with this case, you can utilize that simple formula. Otherwise, so if we go to from this solar system, to a galaxy, you basically going to dealing with this kind of situation. Now, what's the impact? That's going to relate to the biggest problem in the physics, the missing mass or the dark matter problem. So that's basically you can figure out if any mass is missing or there is something wrong with the calculation. Right. So that's basically what I demonstrate. So how can we do this? But the thing is, so when you look at this mass distribution, you have to have that rho, which is the mass distribution function. So when you look at the galaxy, that's very, very hard to find that thing. So luckily we have a Gaia satellite. So by using the latest Gaia satellite data, so we can simulate this Gaia satellite. So we can simulate the Milky Way, and we can calculate this rotation curve. So that's basically what we have. So the flat rotation curve, if you apply this non-spherical model, and you'll get this flat rotation curve. So according to this calculation, there is no mass missing, at least in our Milky Way. So the take-home message is going to be, so the gravity looks simple, but it's really complicated. Okay, thank you very much.